Hi guys, welcome back to this YouTube channel, IBwontcrushyou, and today we are dealing with geometric transformations, and this topic is dedicated only for higher level. And as always, we will go through some problems to make sure that you understand every type of question. So let's get started. Problem 1. A triangle has vertices A with coordinates 0, 0, B with coordinates 2 and 0, C with coordinates 0 and 3. It is transformed to triangle A 0, 0, B 0 and 2, and C minus 3 and 0. A. Describe the transformation that maps triangle ABC to our image ABC. So let's just draw our triangles in the coordinate plane. So these are our triangles. The pink one is the original one and the purple is our image. And we can observe that this side that has three units is in here. And this hypotenuse is in here. So we can observe that our transformation is basically the rotation by 90 degrees anticlockwise about the origin. So this is our transformation. B. Write the corresponding transformation matrix. And in order to do this point B, we have to look for the transformation matrix. And in the booklet, you have 6 transformation matrices, and you have to look for anticlockwise rotation of angle theta about the origin, and it looks like this. So this is the matrix, and now we can substitute our angle, so 90 degrees, so cosine 90 degrees minus sine 90 degrees, sine 90 degrees, and cosine 90 degrees. And you can simply calculate it in your calculator. And our transformation matrix is 0, minus 1, 1, and 0. C. Verify your result by applying the matrix to point B. So basically, we have to multiply our transformation matrix with our point B. So 0 minus 1, 1, 0 times our point B, so 2 and 0. You should remember why the first matrix is our transformation matrix and the second matrix is our point B. You have to think about rows and columns to know why we multiply these matrices like this. And from this, we have 0 times 2, so 0 plus minus 1 times 0, so 0, and here we have 1 times 2, so 2, 0 times 0, so plus 0, and this is 0 and 2, and this is the same as our image of point B. Problem 2. Consider the point P with coordinates 1 and 2. It undergoes 2 transformations. The first one is a reflection in the line y equals x, and the second one is a rotation of 90 degrees anticlockwise about the origin. And in point A, we have to find the coordinates of the image P after both transformations. So let's just draw our coordinate plane and denote our point P. So this is our coordinate plane with our point P. Here we have x1 and y2, and we know that the first transformation is a reflection in the line y equals x. So our line y equals x is of course in here, and our point is reflected in the line y equals x, so our point P is now here. So we have just swapped coordinates. So our point P after this transformation has coordinates 2 and 1. And the second transformation is a rotation of 90 degrees anticlockwise about the origin. So as you remember from the previous task, we have this matrix with cosine and sine. So we have to use it once again. We know that our angle is 90 degrees and it looked like this. So 0, -1, 1 and 0. And of course we are multiplying it with our new point. And here we have 0 times 2, so 0, -1 times 1, so plus -1, so -1, and 1 times 2, so 2, plus 0 times 1, so 0. So we have -1 and 2, so the coordinates of our new point are -1 and 2. B. Find a single 2 and 2 matrix that represents the combined transformation. So let's firstly write down our first matrix, that is a reflection in the line y equals x. So when we have this type of reflection, our transformation matrix is 0, 1, 1, and 0, and we have to multiply it with our matrix that corresponds to our rotation. So 0, -1, 1, and 0, and we can of course calculate our final result in calculator using matrices. So the answer is -1, 0, 0, and 1. So that's our single matrix that represents the combined transformation. C. Show that applying the matrix to P gives the same result as in point A. So we have our point with coordinates 1 and 2. So we have to multiply our point P with our new transformation matrix. So of course, firstly, we are writing down our transformation matrix because of the rows and columns, and then our point P, so 1 and 2, and we can of course calculate it using our GDC, and the result is -1 and 2, so it's the same as in our point A. Problem 3. The square with vertices 0 and 0, 2 and 0, 2 and 2, 0 and 2 undergoes the transformation given by matrix M 1, 1, 0, 1. A. Find the coordinates of the transformed vertices. So we have to calculate each transformed point, so every image of our original point. So basically we have to multiply our matrix M with our first point, then our matrix M with our second vertex, and so on. Here we have 2 and 2, and here we have M times 0 and 2, so we have to calculate everything. You can of course do it using your calculator. So here we have coordinates 0 and 0, and this is of course because our point and the origin doesn't change because 0, 0 are unchanged. Then we have 2 and 0, then we have 4, 2, and then 2 and 2. So these are our coordinates of the transformed vertices. B. Sketch both the original and transformed square. So we have to just draw our coordinate plane and then denote all of these points. So these are our figures. The purple one is our square, and the pink one is our transformed square. And in C, we have to decide what type of quadrilateral is the image and justify our answer. So we can observe that these two sides are parallel to each other, and these as well. So our quadrilateral is parallelogram because it has parallel sides. Problem 4. A transformation matrix is defined by T, 2, 1, 0, and 1. A. Find the eigenvalues and eigenvectors of T. So in order to do this, firstly, let's just draw two vertical lines, and here we have our 2. So the same as in our transformation matrix. However, from the first value we have to subtract lambda, then we have 1, so we leave it as 1, then we have 0, and from the last value we have to subtract lambda as well, and this is equal to 0. So now we have to multiply this with this and then subtract 1 times 0. So in the bracket we have 2 minus lambda times, and in bracket 1 minus lambda minus 1 times 0, so just 0, and this is equal to 0. So now we have to multiply the values in our brackets. So firstly we have 2 times 1, so 2, then 2 times minus lambda, so minus 2 lambda, then we have minus lambda times 1, so minus 1 lambda, and then we have minus lambda times minus lambda, so plus lambda square, plus lambda squared, and this is equal to 0. So we can change the order. So first we have lambda squared, then we have minus 3 lambda, and plus 2 equals 0. So now we can solve our equation in order to find lambda, and when we have to find eigenvalues and then eigenvectors, we should have basically we have to have two answers, so 2 lambdas, and we can use solver, graph function, or polynomial in order to find these values. Okay, so these are our lambdas. Lambda 1 is 1 and lambda 2 is 2, and now we have to find eigenvectors. So let's start with lambda 1, that is 1. So we have to substitute 1 into this. So our matrix is 2 minus 1, so 1, then we have 1, then we have 0, and then we have 1 minus 1, so 0, and then we have to multiply it with x and y, and this is equal to 0 and 0. So now we can multiply 1 times x, so x, plus 1 times y, and this is equal to 0. So now we can move our x from the left hand side to right hand side. So y equals minus x. And in order to find our eigenvector, we can substitute, for example, 1. So when when y is 1, our x is minus 1. So this is our first eigenvector, and we have to do the same with our lambda 2, that is 2. So here we have 2 minus 2, so 0, then we have 1, then we have 0, then we have 1 minus 2, so minus 1. And of course, times our matrix x, y equals matrix 0, 0. And the same, here we have 0 times x plus 1 times y, so plus y equals 0. So of course 0 times x is just 0, so y is 0. So we are given that y is 0, and we can substitute as x any value, so for example 1. So this is our first eigenvector that corresponds to our lambda 1, that is 1. And this is our second eigenvector that corresponds to our lambda 2, that is 2. And of course, I substituted in here, for example, 1, but it can be any multiply of this and this eigenvector. So it can also be eigenvector 1 and minus 1. Here it can be 3 and 0, and so on. It has to be just a multiply of this eigenvector. And in B, we have to interpret geometrically what the eigenvectors represent in terms of invariant directions. So let's maybe start with this one. We have eigenvector 1 and 0. So this is basically an invariant direction scaled by factor 2. So it means that that this is stretched, and this eigenvector, this is basically an invariant direction scaled by 1. So it has unchanged length, and both these eigenvectors are the invariant directions of the linear map. So we can write down something like this. C. Use GDC to iterate the transformation on the vector 1, 0, 5 times. What do you observe? So in here, we have to just write down our, firstly, transformation matrix to the power of 5, because in here we have iterate the transformation on the vector 5 times. So our transformation matrix is 2, 1, 0, 1. So 2, 1, 0, 1 to the power of 5, and then times our vectors, so 1 and 0. So we can simply calculate it using our GDC, and the answer is 32 and 0. So we have to also answer what do you observe. So we can observe that this iterating rapidly stretches components in the direction of the eigenvector with eigenvalue 2. And D. Discuss how this relates to stability of directions under repeated transformations. So when our eigenvalue is greater than 1, so in our case we have eigenvalue 2, so this is an expanding direction, and repeated application just makes components along the eigenvector grow exponentially. And our eigenvalue, that is 1, is neutral. Basically, it neither grows or nor decays. So for many initial vectors, repeated application will make the image vector become increasingly aligned with the dominant eigenvector. So here our eigenvector 1 and 0, and this is magnified by the dominant eigenvalues power. Problem 5. A transformation maps the unit circle x squared plus y squared equals 1 to an ellipse given by x squared over 9 plus y squared over 4 equals 9. A. Find a matrix M that performs this transformation. So in other words, we have to go from this to this somehow. So the first thing that we can observe that we have in numerators letters squared. So we have x squared and y squared, and in the denominators we have values that have values that can be squared to give us these values. So basically 9 is 3 squared and 4 is 2 squared. So we can write down the fractions in this form, and here 2 squared equals 1, and we know that when we have both values in our fraction squared, we can have a bracket and square the whole fraction, and the same in here. And now we know that our transformation matrix M has 3 that corresponds to x and 2 that corresponds to y. So M is, and our first value has to be 3 because when we are multiplying our first row from transformation matrix with some point, so it has to be the first value in order to correspond to x. Then we have 0, and then we have 0, and then we have 2 because 2 corresponds to y, and when we are multiplying transformation matrix with a point, so it has to be in here. So that's our transformation matrix. And in B, we have to apply M to the point 0.6 and 0.8 and verify that the image lies on the ellipse. So firstly, we have to just multiply our transformation matrix, so 3, 0, 0, 2, with the point 0.6, 0.8. So we can simply calculate it using our calculator or by doing it by hand, because here we have 3 times 0.6 plus 0, so it's just 1.8, and then we have 0 times 0.8 and 2 times 0.8, so it's just 1.6. So this is the result, and we have to verify that the image lies on the ellipse. So we have to substitute this point with these coordinates into our equation of the ellipse. So 1.8 squared over 9 plus 1.6 squared over 4. And we have to calculate it. So the first value is 0.36 and the second value is 0.64, and of course the result is 1. So as required, so the image lies on the ellipse. And that was the last problem from this topic, geometric transformations. And if you found this video helpful and useful, you can share it to your friends. Of course, you can subscribe to this channel and leave a thumbs up. And in case of any questions, you can write them down below in the comments or via my mail. And thank you so much for watching. See you!